Section 2.5, Physical Applications. In this section, we'll look at two different applications. The first one involving mass given a density function, and the second one involving work given a variable force. We'll start with mass and density. The simplest example is a thin rod or wire, which is depicted here in this XY coordinate axes. The thin rod or wire is oriented on the x-axis between A and B, as shown here. Now, if this rod or wire has a constant density, all we have to do to calculate the mass of this rod is to multiply the length of the rod, B minus A, times the constant density. In this case, they're using the Greek letter lowercase rho. So it's just a multiplication problem. But if the density of the rod varies from point to point, we're going to give that a function named rho of x for the density of the rod at any given point x. In other words, for each point we pick between A and B, if we took this x value or this x value or that x value or any x value between A and B and plugged it into a rho of x, we would get a different density for the material that makes up this rod. Now, what we're going to do is very similar to what we did back in Calculus 1 involving areas under curves. We're going to take that region from A to B and we're going to split it up into a bunch of subintervals like this. And maybe A is x sub 0, and this here would be x sub 1, and x sub 2 would be right there, and so on and so forth. And then we'd get eventually to x sub I minus 1 and x sub I. And then we would look at just this one interval here that I'm highlighting in blue, and we could approximate the mass of that part of the rod by simply taking some point in this little region, any point in that region. We can call that x sub I star, as you see right here. So if this is x sub I star, we could put that into rho, the function for the density. That will tell us the density at that point for the rod. And then we could multiply it times the distance x sub I minus x sub I minus 1. So this is very similar to what we have over here, where we multiplied the distance across the entire rod times the constant density function rho. Here, we're getting a constant density over just the highlighted blue portion. So that'll give us an approximation of the mass of just this part of the rod. And of course, we can repeat this all over the rod for all the different intervals that we've set up. And then what do we need to do with all of them? We need to add them up. So that's what we're seeing over here. So in the upper right-hand corner, we have this bit right here. That's an approximation of the mass of the rod between x sub I minus 1 and x sub I. We can rewrite this portion as delta x. So now we are here for the approximate mass of that part of the rod. And as I mentioned a moment ago, we want to add up these approximate masses across the entire rod, which is what we have over here. Next, we want to take a limit as the number of these little intervals goes to infinity, just like we did in Calc 1. If you remember, we had an interval from A to B along the x-axis, and then we had a function f above it, and we broke this up into a bunch of subintervals, and we evaluated f to get the heights of our rectangles, and we multiplied them to get a bunch of rectangular areas that we added up. That's really the same setup as what you see right here. What we had was f of x sub I star times delta x, where I is going from 1 to n. And then the next thing we needed to do is we needed to take a limit as n goes to infinity, and that gave us the integral, or area under the curve, from a to b of f of x dx. Well, if you look at what we have here, it's identical, except for instead of integrating the function f, which was that curve in this graph, we're now integrating the density function rho of x. So in the gray box, it kind of goes through all the specifics on that. You can pause the video and read that, but it basically presents what we just showed. And let's go ahead and do example one. It's relatively straightforward. Consider a thin rod oriented on the x-axis from x equals pi over 2 to x equals pi. If the density is given by rho of x equals sine x, what is the mass of the rod? So based on what we just derived up there, the mass will equal the integral from a to b, integrating the density function rho of x dx. And so we have our limits of integration from pi over 2 to pi. Rho of x is sine x as such. And here we have a pretty straightforward Calc 1 integral. And there you have it. So with that first example, we looked at the linear case where we just had a very thin wire that we were finding the mass of using a variable density function. Moving to a two-dimensional disk of radius r, we're going to find its mass, but we have a couple of prerequisites to be able to do this. Namely, we're going to be dealing with a radial density. Basically, we assume that the density varies with respect to the disk's radius, meaning it might be less dense at the center and the density increases as we move away from the center along a radius. And we're going to assume that the density is given in terms of mass per unit of area, whereas in the last one, the density was just given at a specific x value along the wire. So ultimately, what we're going to do here is we're going to multiply an area by an area density, thus giving us the mass of that portion of the disk. So again, the density of the disk is going to be given to us as a function rho of x. And as I mentioned a moment ago, we're going to kind of think of this as we move out along the x-axis, our density maybe increases or decreases or just changes with respect to changes in x. That means that for any given radius, like right here, the density on that circle would be constant. That's what they mean by radial density. And so just like we did with the rod earlier, we're going to take our x-axis from 0 to r, and we're going to split it up into a bunch of subintervals. And one of them right here, say, is going to be x sub I minus 1, and there's x sub I. And I probably can't draw this very well, but imagine the circular region or washer that we get between those two values of x, and that gives us something like this. Now, we want to take this area that we have here, and we're going to multiply that times the variable density function rho of x. So first we have to come up with that area. Well, kind of like we did with washer method, we're going to take the outer, the area of the entire circle, right? This whole thing, which is right there, and then subtract out the white inner area, which is right there. From there, we're going to do a little bit of algebra. We're going to factor out the pi going from here to here. We're going to factor difference of squares from there to there. We're going to notice that x sub I minus 1 is going to be delta x. And so here now we have this formula for the area of, say, ring number I. And we could repeat this for any ring on this circular disk. From there, we're going to let x sub I star be the average of x sub I and x sub I minus 1. In other words, it's going to give us a point halfway in between right there. So then we can take our a sub I, multiply it by 2 like this, but also divide it by 2, right? Those 2's cancel, take us back to where we were. But then we can replace this guy in yellow with this right here. And when we do that, we end up with 2 pi x sub I star, right? That's what's replacing the yellow right there. So we have x sub I star delta x. And that brings us to this bit here in blue. So that gives us the area of the washer number I on our circular disc. Okay, we could do it for the first circular disc, the second, the third, all the way out to the nth circular disc, or sorry, circular washer, I should say, filling up this disc. So from there, what do we need to do? Well, kind of like we saw earlier with the linear case, we need to multiply this area that we have in light blue, which is right here. We have to multiply it by the density at that point, x sub I star. And that's what I'm highlighting here in gray, if you will, down at the bottom of the screen. So that gives us an approximate mass of this washer, of washer number I. And of course, the next thing we do is we add it up to all the other density times areas of all the other washers, as you see here with the summation. And finally, we take the limit as the number of these washers goes to infinity, and we end up with this integral here. And that's how we're going to find the mass of a circular disk, where rho of x is the radial density of the disk, and of course r is the radius. Let's go ahead and do an example. Example 2, let rho of x equal the square root of x, represent the radial density of a disk, calculate the mass of a disk of radius 4. So we're taking the mass to be the integral from 0 to r, 2 pi x rho of x dx. Again, as we just discussed above, this part in green gives us basically the area of our washers, and then we're multiplying each one of those areas by our radial density. So that's what we're going to integrate. And we get the integral from 0 to 4 in this case, 2 pi x square root of x dx. We can, of course, take the 2 pi out, rewrite x square root of x as x to the 3 halves dx. Now we have a very straightforward Calc 1 integral. And that simplifies down to 128 pi over 5. Now, a common question at this point is, well, okay, great, we can find the mass of a little thin, infinitely thin wire along the x-axis between A and B, as we did in the first example. And then with this second example, we found the mass of a circular disk that has variable radial density. But what if I just want to find the mass of some random plate, that thin plate that has whatever shape? It's not circular, and maybe it varies its density across this plate in some unpredictable ways, unlike the circular nature of the one we just did. Or what if I have a three-dimensional figure and I want to go ahead and find the mass of that given some density function? So those are great questions, and they can be answered using calculus, but we need multivariable calculus to do that, because we have more than one variable when we look at our plate as a non-circular plate with some other density function other than radial density. The density will change as x changes and y changes along that plate, right? If this was the plate, here's your x, here's your y, and at each point you're getting a different density dependent on changes in x, changes in y, we need more than one variable calculus to deal with that. And that is something that gets dealt with in a multivariable calculus class. So we're kind of laying the groundwork for that moving forward. Okay, for this next application, we're going to consider an object that's being pushed along some distance. We'll just call that distance d. And we're applying a force in the direction of motion, call that capital F. And so as we push this object from, A to B along here, we're applying the force F the entire time, a constant force, and a certain amount of work is being done. And we define the amount of work done by applying a constant force F to our object over a displacement or distance of d. We define that work as being the product of the force and the distance that we've pushed this thing. Okay, so that's for a constant force. So let's just start with that for now. So as far as units that we'll encounter for dealing with work and force and displacement, if we're looking at the metric system, we're going to be using newtons for force, meters for displacement, and that will give us joules. 1 joule is equal to 1 newton of force times 1 meter. And for US customary system, we'll be using pounds for force, feet for distance, and the units for work will be foot-pounds. So all that said, let's look at example 1. Find the work done if an object moves 5 feet along a line while subjected to a constant force of 100 pounds in its direction of motion. So the work done, because we're dealing with a constant force F and it's in the direction of motion d, we're simply going to multiply our 100 pounds of force times our 5 feet and end up with 500 foot-pounds. Pretty straightforward, just kind of getting used to the basics here. And from there, for part B, an object moves 25 meters along a line while subjected to a constant force of 4 newtons in its direction of motion. So again, the work is going to involve a constant force times its the distance traveled, which here this is 4 newtons times 25 meters, and that will give us 100 joules, which, by the way, a joule is sometimes referred to as a Newton meter, kind of like up here, this was foot-pounds, joules, Newton meters. Anyway, so what I'd like you to notice before we move on, because there's no calculus here, obviously, but I do want you to realize that you can kind of imagine these two values as representing an area. And what I mean by that is if we look at our 5 feet that our first object was moved when applying a force of 100 pounds, really that 500 is simply the area underneath the force function, right? From 0 to 5. Okay, in other words, we could have, it would have been silly, but we could have gotten the work by integrating the constant force of 100 along, we'll just say the x-axis, from 0 to 5, and we would have gotten that area, which just happens to be the same value as the work done. Okay, the same thing on the next one, right? We could have integrated from 0 to 25 the force, the constant force of 4 dx, and that would have given us our 100 joules. Okay, now there's a reason why I'm bringing this up and kind of connecting it with integrals and area, because the next thing is to say, okay, what happens when the force applied varies as the object moves. Okay, so what I want to picture here is that we now have, say, an object that's moving from point A to B along the x-axis, well, in the positive direction, and let f of x, maybe we'll draw something like this, f of x is the variable force acting on our object, and we're going to assume f is continuous. Then we can split up this region AB into a bunch of subintervals, and we can grab, I don't know, let's say this one, call that x sub I minus 1, and call this x sub I, and then pick an x value in between here, which any x value in that little subinterval, we'll call it x sub I star, and we can get the value of the force at that point, right? That's going to be f of x sub I star. So that right there is, we can kind of think of that as a little constant here, right? Imagine a little horizontal line there over this one interval. Okay, so again, this right here is now a constant force because I've plugged in a specific x value into my variable function for the force f. And then if I multiply that by the width of my little rectangle there, we'll just call that delta x. Okay, that's basically a change in x. That's a little distance. We're multiplying a constant force times the distance. That's an approximation of the amount of work done just on that little ith subinterval, which is equivalent to the area of this rectangle, which is what we were talking about back here as well. And so once we have that, we can get an approximation for the work done along the entire distance from A to B by summing each one of these x sub I stars plugged into our function times delta x, I going from 1 to n. And then, of course, once we've added up all of those, we can then take a limit as the number of these little regions goes to infinity, right? Each one of these little rectangles, really kind of similar to what we did with area under a curve from Calc 1, I equals 1 to n of f of x sub I star delta x, and that's going to be the actual work done by the variable force in moving our object from point A to B. And so this, of course, becomes the integral from A to B of f of x dx. And so that's just a very quick kind of run through where they're coming up with this. The work performed moving an object along the x-axis from A to B by applying a force of magnitude f of x, this is again a variable force, it changes depending on which x value you pick, is simply a matter of integrating the variable force from A to B. So if we look at example 2, find the work done by the force of f of x equals 1 over x squared newtons in moving the object along the x-axis from x equals 1 to x equals 10, we're going to get the work by simply integrating from A to B f of x dx, which in this case is going to go from 1 to 10. We're going to have 1 over x squared dx. Again, pretty straightforward Calc 1 integral. And we end up with 9/10 joules. Okay, so now that we've established how to calculate the work done in moving an object using a variable force, the rest of the examples in this section are simply going to be different types of situations where we have variable forces involved and we'll be calculating the work done. So the first type of question is going to involve Hooke's law. Hooke's law has to do with springs. Hooke's law says that the force required to hold a stretched or compressed spring x units from its natural length is proportional to x. So f of x is equal to kx, where k is a positive constant called the spring constant. So if we imagine a spring, I'm going to draw a couple of these. Let's just put 0 right here, let's say. And maybe our spring in its natural length looks like this. Okay, so meaning when I say natural length, I'm basically saying that there's no force being applied to it, right? It's just that's where the spring is, that's how it looks. And then we can either compress the spring by pushing it that way, or elongate the spring, stretch the spring by pulling it that way. So maybe that same spring, when it's elongated, ends up going all the way out to here. Now, the reason I've chosen to draw it this way is back here you'll notice that we have x units from its natural length. That's what this x is here. So the distance from here to here, right, from its natural length out to x, this is our x units from natural length. And basically what Hooke's law gives us is that if we've got our x along the horizontal axis, so this is the amount stretched or compressed, and the force is on the vertical axis, what Hooke's law basically says is that to stretch, let's say we're stretching this a certain distance x, then the force done to hold that out there is going to be kx. And of course, this holds for when we compress the spring x units as well. So let's go ahead and look at example 3. A spring has a natural length of 1 meter. A force of 24 newtons holds the spring stretched to a length of 1.8 meters. They want us to find the spring constant and then find how much work will it take to stretch the spring 2 meters beyond its natural length. So first we're going to find the spring constant. So from Hooke's law, we have that the force required to stretch the spring x units beyond its natural length is simply kx. And they're telling us in the question that it takes a force of 24 newtons to stretch the spring to a total length of 1.8. This 1.8 here is 0.8 units beyond natural length. Or I should say meters, not units, right? Meters beyond natural length. So that's our x. So we're going to put that right here, 0.8. And we can solve. K will equal 24 divided by 0.8, and that's going to be 30. And notice that we have newtons divided by meters. And so this is our spring constant. So the force required to stretch or compress the spring x units from its natural length is, I'm going to use a capital F for force, f of x is equal to 30x. So that is our force function for this particular spring. Now, in part B, they want us to find the work it will take to stretch the spring 2 meters beyond its natural length. So we're going to let x equals 0 be the position of the end of the spring when it's unstretched or compressed. So x equals 0. In other words, it's basically the picture up here, right? We're not applying any force to the spring whatsoever. We're not pulling it. We're not pushing it. We're just leaving it as is, and we're having it start at x equals 0. So the work done by the force F is going to take, so we want to find, here, let's write this. So the work done by F on the spring from x equals 0 meters to x equals 2 meters is, well, from above, right? From the very top of the page there, we're going to be integrating from a to b f of x dx. So for us, that's going to look like the work is going to go from 0 to 2, right? We're stretching from 0 meters to 2 meters, and our force function is 30x dx. Needless to say, the setup was really what this was all about, because this is a really straightforward integral, and we're getting 60, that's a 0 down there, 60 joules. And so we do have one more question here. How far will 45 Newton force stretch the spring? So as you're working on these, you want to really kind of get it clear in your head. Are they asking for work, or are they asking about force? So part B is definitely a work question, right? It's right there in the question. And then part A, we didn't really do anything with work because we were just finding the force function, in particular, finding the spring constant. But in part C. But in part C, there is nothing involving work. They're just giving us a force here, but we know that the force is equal to 30x, where x is the distance beyond the natural length of the spring that this spring is being stretched. So I think we can say, well, let's put 45 here, right? If we apply a force of 45 newtons, how far beyond the natural length will the spring stretch? That's a matter of just finding x. And so x is equal to 45 over 30, which is equal to 1.5 meters because we're dealing with newtons. All right, let's look at another one kind of similar to this. Example 4, 18 foot-pounds of work is required to stretch a spring 4 inches from its natural length. Find the work required to stretch the spring an additional 3 inches. So they want us to find work, which will be the integral from A to B of kx dx, right? Again, this right here is our capital F of x. This is our force required to stretch or compress a spring using Hooke's law, right? That is Hooke's law. So that's what we're going to integrate. Now, if you read this again, you'll see that they're giving us right here, that is work right there, 18 foot-pounds of work. So that's our W, is required to stretch a spring 4 inches from its natural length. So we'll have to talk about that for a moment, but that's going to have to do with the limits of integration. Find the work required to stretch the spring an additional 3 inches. So what I'm saying is that we have 18 for our work. We're integrating from natural length to some value here, which I want to talk about in a moment. And then we have kx dx. Now, the reason I'm pausing here is I want you to notice that they told us that 18 is measured in foot-pounds, but the spring is stretched 4 inches from its natural length. So we need to reconcile these different units. So 4 inches right here is the same as 4/12 feet, or 1/3 of a foot, right? And the reason we need to do that is because 18 is in foot-pounds, so we need to convert our distance that we've stretched our spring beyond its natural length to feet. So my upper limit of integration here is 1/3. So just to kind of read through that first sentence again, we have 18 foot-pounds is the work done in stretching the spring from its natural length to 1/3 of a foot beyond. Kx is our Hooke's law, right? Our force, that our variable force that we're integrating, dx. And so now we can solve for k. We can find our spring constant because we can integrate. We're going to get k over 2x squared evaluated from 0 to 1/3. I could multiply the 2 to the other side to get a 36 here, and get a k times 1/3 squared minus 0 squared, which will give me 36 equaling 1/9 k. If I multiply both sides by 9, we get k is equal to 324. And so there's our spring constant. So the force required to stretch or compress the spring x units is going to be capital F of x. Instead of kx, we now know that it's 324x. So we get that from the given information regarding the work, and we just found the variable force for stretching or compressing our spring. Now, they want us to find the work required to stretch the spring an additional 3 inches. So they want us to basically figure out the work required to stretch spring from 4 inches to 7 inches, an additional 3 inches. And again, we have to think about changing our units to feet, because we got this function down here in terms of feet, right? So we're going to get that the work done is going to be the integral from 4 inches to 7 inches. Well, that's 4/12 of a foot to 7/12 of a foot. And then we have our force function, 324x dx. And again, straightforward integral, we're going to get 162x squared evaluated from 4/12 to 7/12. And that's going to give us 162/49 over 144 minus 16 over 144. Gives us 33 over 144, which results in 297 over 8 foot-pounds. And if you put that into a calculator, you get approximately 37.125, or that's exact. That's not approximate. Exactly 37.125 foot. So that's utilizing Hooke's law. Let's look at another example involving a variable force to determine the work done. This is not involving a spring. This will be a little bit different. Example 5, a 5-pound bucket is lifted from the ground into the air by pulling in 20 feet of rope at a constant speed. The rope weighs 0.08 pounds per foot. How much work is spent in lifting the bucket and the rope? Okay, so I'm going to draw a little figure here. So here's the ground. Here's, I don't know, the side of a building. And way up here, we've got, I don't know, some kind of pulley system with a rope, a blue rope coming down like this, and it's connected to a little bucket, maybe like that. I don't know if that looks like a bucket. And pretend that rope is straight down. Here, I'm going to redo it real quick. The way we're going to deal with this is first realize, and right, this is being pulled, right? There's a person up here pulling it like that. So we're dealing with 20 feet from top to bottom, right? So from here to here, that entire distance from there to there is 20 feet. And we're going to first, just kind of thinking about this, if we're doing work, we know we have to integrate a variable force. Now the bucket is a constant weight. So let me write a couple things and I'll explain as we go. But the bucket has constant weight. So work done lifting it is simply the weight of the bucket times the distance, right? The weight is the force. That's what's pulling down, right? The heavier it is, the more it's pulling down. That is our force. And they're telling us in the question that we have a 5-pound bucket and it is being lifted a distance of 20 feet. So just the bucket by itself, if there was no rope involved, we have 100 foot-pounds. That's the work done in lifting the bucket alone. Okay, now, where does the calculus come in here? Well, the weight of the rope varies. Why? Think about that while I write. So when you start this exercise of pulling this bucket up, you have a lot of rope, right? You have all of this rope that's hanging over, and the weight of that rope is making the whole system heavier. But as you pull more of the rope up onto the top of the building, and you have less rope hanging over the edge, that means there's less weight hanging over the edge. So as you pull the rope higher and higher, you're having to pull less weight up. So there's less work to be done. So let's introduce a variable here. Let's talk about maybe the distance that the bucket's off the ground. So I made the bucket super close to the ground here, but I'm going to call that distance x. And that's going to leave this red distance to be 20 minus x. And so the length of the rope is going to be 20 minus x. Now, I know I've got my little handle there and I didn't make that look quite right. Let's fix that. Let's just say that I should have done more, something like that. I guess I should say that x is the height of the top of the bucket, right? So there. Okay. Anyway, same idea. the length of the rope is 20 minus x, and x is constantly getting longer and longer, and the rope is getting shorter and shorter. Yeah, up until 20 when the whole thing's over with. So let's write a couple things. When the bucket is x feet off the ground, the remaining part of the rope still being lifted has a weight of, well, we know that the amount that still needs to be lifted is 20 minus x, right? That red distance. And they tell us in the question that this rope weighs 0.08 pounds per foot. So we multiply 0.08 times the length of rope, and that's going to be pounds. So that is our force that's being exerted just by the weight of the rope, right? It's again the weight per unit of length, and then the length of the rope is 20 minus x. So we can find the work lifting just the rope is going to be the integral from 0 to 20, right? We've got to lift this rope 20 feet total. In other words, our x's, right, are going to start at 0 when the rope is way down on the ground, and it's going to end, x will end at 20 when the bucket is up on top, right? Look at the green length there at the bottom. That's our x going from 0 to 20, and we're integrating 0.08 20 minus x dx. So there's the setup. The rest of this is going to go pretty quickly. I'm just going to distribute the 0.08 and then integrate, and that looks like this. And we end up with 16 foot-pounds. The total work lifting bucket and rope is 100 foot-pounds plus 16 foot-pounds, which gives us 116 foot-pounds. So it's kind of an interesting problem because you have to deal with both a variable force when lifting the rope and a constant force when dealing with just the bucket. Let's look at one more. Example 6. A tank has the shape of an inverted circular cone with a height of 10 feet and a base radius of 5 feet. It is filled with a certain type of oil to a height of 8 feet. The oil weighs 57 pounds per cubic foot. How much work does it take to pump the oil to the rim of the tank? All right, so what we're going to do here is we're going to imagine that the oil inside this tank is divided into a bunch of slabs going up the y-axis from 0 to 8. And an example of a slab is over here in, I don't know, whatever color that is. That's an example of a slab. And if you think, wow, that kind of looks like a disc from our disc method business, yeah, that's the idea. Imagine a bunch of those slabs of oil. The volume of a typical slab between y sub I and y sub I plus a change in y. So real quick, over here, I'm calling this delta y. And so what we're saying is the bottom height of this little slab is y sub I, and the upper part, or the top of that slab, is y sub I plus delta y. Okay, so that's what that's about. But the volume of this guy is going to be, well, we know how to find the volume of a cylinder. We're going to call that V sub I, the volume of the slab number I, right, the ith slab. We have pi times the radius squared times the thickness of the slab. Really, that's just the cross-sectional area, right, like this, times the height of that cylinder, right, that little flat-ish cylinder thing. So we've got some similar triangles going on here. From the question, they're telling us that the radius up here is 5, and of course, the height is 10. And so you'll notice that this radius is always 1/2 of the y value, in this case 10, right? That's how we're getting the 5. So even when we go down here, the radius right here, I don't know if you can see that, that right there is going to be 1/2 of y sub I because of similar triangles, right? We have a similar triangle down here to the triangle that we get from the entire cone. So that's going to give us our radius, which is good because now we can say that V sub I is equal to pi 1/2 y sub I quantity squared, and the thickness is delta y. So maybe we rewrite that as pi over 4 y sub I squared delta y, like that. And that's going to be in cubic feet. So that is the volume of that slab. And we can do this all the way up and down our cone of oil, if you will. Now, the force required to lift this slab is equal to its weight. Well, how do we get its weight? Well, we have its volume. If we knew the weight per volume, per unit of volume, we'd know the weight. And we have that right up here. So I'm going to call that the force of slab y sub I is going to equal 57 times our volume, which was pi over 4 y sub I squared delta y, and that's in pounds. All right, we're making some progress here. So we have the force required to lift a slab, or an example slab, if you will, and that's simply its weight. Now, the distance, we have to think about how far we need to go. So the distance through which F y sub I, right, this force must act to lift the slab to the rim of the cone is going to be approximately 10 minus y sub I feet. So again, we chose our y sub I right here at this height right there. And so if the whole cone is 10 feet high, we just need to lift it 10 feet minus how high the slab already is, which is y sub I. So that seems to make sense. And from there, we can notice that so the work done lifting the slab is approximately, call it W sub I, right? We're just lifting slab number I. It's approximately equal to our force times our distance, right? So our force is 57 over 4 pi y sub I squared delta y, and that's multiplying our 10 minus y sub I. Again, this is force, the weight, and this is the distance that it has to be moved. All right, so kind of technical, but we're actually getting close to where we need to be. Now, if there are n slabs between 0 and 8, that means we're going to need to add up all this work done. So let's see. If there are n slabs between 0 and 8, then the work done lifting these n slabs is approximately the sum of the work done lifting each slab, where I equals 1 to n. And of course, we have that expression from above. We're going to sum I equals 1 to n of 57 pi over 4 times, I'm going to change the order here just a little bit. I'm going to put 10 minus y sub I there and put the y sub I squared with the delta y in back. Really, the main reason I'm doing that is if we have the delta y in back, when we do the next step, that's going to become a dy, and then we'll be ready to integrate. So there we have the approximate total work done in moving all n slabs to the top of the rim. So the work done in pumping the oil to the rim is the limit of this sum as n goes to infinity. And of course, definition of a definite integral, this becomes the integral from 0 to 8 of 57 pi over 4, 10 minus y times y squared dy. Of course, the 57 pi over 4 is a constant, and we can distribute the y to get 10y 10y squared, I should say, minus y to the third dy. When we integrate this, we're going to get 10 thirds y to the third minus 1/4 y to the fourth, and integrate from 0 to 8. Obviously, plugging in 0 is going to zero everything out. Plugging in 8, we get approximately 30,561 foot-pounds. So that one gets pretty technical there, but it's just another example, really, of a variable force, integrating a variable force function, right? That's basically what we had back here. This was a variable force function that we're integrating to get the work. And in this case, it was a matter of creating a Riemann sum, right? That's what we ended up with right here, and then letting the limit as the number of the slabs goes to infinity. So there's that one, and that'll finish it off for that section.